Hello everyone. In this video, we are going to discuss about the pipelining, performance, execution, and computer architecture and organization. In the previous video, we discussed about the introduction of pipelining and some of the concept related to the interface. What is the difference between pipelining and non-pipelining? And in this video, we are going to evaluate the performance with respect to pipelining as well as the non-pipelining thing. So now let's start with the video. So we are going to evaluate from the perspective of the performance and performance execution oblique evaluation will be taken here into the account. So performance evaluation will be done. So consider K segment pipeline with cycle time TP used to execute the end task. So you can consider that there are K segments which are there in the pipeline and these pipeline segments are going to have the cycle time that will take TP to execute the end tasks. So end tasks are there, TP is the cycle time and K is the number of segments in the pipe. The very first task in the pipeline execute in non-overlapping manner because there is no other one to enter. So the very first one will execute in the non-overlapping manner so that it will take the K cycle to complete the execution and the remaining n minus 1 task. So if we are having total n task and the very first task is going to execute solo in a non-overlapping manner, the n minus 1 remaining tasks are going to appear and emerge in the pipe at that rate. So n minus 1 task will take n minus 1 cycles to complete the execution. Now, the total time required to complete n task in K segment pipeline is given by this formula, which is written in the line number 4. That is ET, that is the execution time, equal to K multiplied by TP. TP is the cycle time, and we are going to consider the first execution of the instruction in the non-overlapping manner. That's why we are taking K multiplied by TP into account. Then we are going to add for n minus 1, which are going to take the similar kind of time, that is the TP. Okay, so now if we take the TP common out of it, we are going to have the formula as K plus n minus 1, and the overall thing will get multiplied to TP. There K are the stages or the segments, N is the task, and TP is the cycle time in the pipeline. So this is the performance of the pipelining thing. Now, while doing the performance execution of the evaluation, I will write here, we are going to get the gain understanding. So here the gain is represented by S. Let's go to point 5. Consider a non-pipeline processor which is going to execute n task. Here we are talking about the non-overlapping execution of n task. Here every task will execute of its own without in any sharing manner. So it will take Tn amount of time to complete the execution. So every instruction will take Tn amount of time. So the total time will be counted as n multiplied by Tn because there is no sharing. Now we are going to compare the pipelining processor and the non-pipelining processors by the value of gain, where we are going to consider this particular formula, that is pipeline performance upon non-pipeline performance. So here this gain, that is S, is given by the pipelining performance by non-pipelining performance. So pipelining performance will be N into Tn, non-pipelining performance and the non-pipelining performance are going to get in the scenario here. So what we are going to do here, we are going to get some more kind of mathematics here. So pipelining performance will be like 1 upon the execution time of the pipelining thing and 1 upon the execution time of the non-pipelining. Okay, so now if you solve this thing, this will go up and this will come down. So it will be like ET of a non-pipeline upon the ET of the pipeline. And when you just put the value of the formulas like N into Tn, this is for the non-pipelining and this is for the pipelining as we discussed just now. So this is the final gain formula for the pipelining versus non-pipeline. So where N is very large, you are going to see the difference But when n is not very large, you will not see that much difference, because the values will not have that much kind of differences in the numerator and the denominator. So this is about the performance evaluation. Now we are going to understand the delays that happen in the pipeline, and there are sometimes uniform delays and sometimes there are non-uniform delays. So in uniform delays, all the stages that we have in the execution of the instruction maintain the same amount of delay. It means the fetch, decode, execute and write back all are having the same amount of delays. So now we understand that we are having stages, and in between stages we are having interfaces. So for one thing to get executed fully, we are going to encounter the delays encountered by the stages as well as with the interfaces. So if there are no interface, we are going to consider there is no interface, that will be counted as the stage delay. But if there is buffer and there is a delay, then it is going to get executed as the stage delay plus the buffer delay. Okay, so now TP equal to stage delay and TP equals to stage delay plus the buffer delay. Buffer delay when we are going to have any kind of interface in between, and the other thing is like when we are going to have the non interface thing. So let's understand with this example. Suppose we are having these stages and intermediate thing here. So let's say all the stages are in the uniform delay pipeline. So stages will have 2 nanosecond, let's say the delay, and the interfaces are having 1 nanoseconds of delay. So totally it will be, if there is no interface, then the total stage delay will be 2 plus 2 plus 2 without any kind of stage delay. That is this formula. But if we are having the stage delay, it will be 2 plus 2 plus 2 plus sorry, here we are not going to calculate for the entire thing. We are going to calculate the delay for only one segment. So we are going to change this formula. Stage delay here will be 2 nanoseconds, because we are going to talk about only the stage. I was calculating for the entire pipeline. Here we are only focusing on the one stage. Now the stage plus buffer delay will give us 2 plus 1, that is 3 nanoseconds. So 3 nanoseconds will be the entire thing as the delay with the uniform time delay. Okay, so if you want to calculate the execution time, here you will have k plus n minus 1 multiplied by the TP. So here you can see that you are having 3 cycles, let's say. So we are having the value of k as 3 plus how many instruction? Let's say there is only one instruction. So 1 minus 1 and TP. TP will be the execution time here, the cycle time, which is accounted as 3 here. So we will have 3 here, because it is having delays as well. So it will be 3 multiplied by 3, that is equal to 9. That will be our answer. So in this particular case, we are including the buffer or latch or register or the pipeline interface. If you don't want to include it, you can multiply it by 2 and then you will have your answer. Now we are going to focus on the non-uniform delay. In the non-uniform delay, every stage will have different kind of amount of delays. So different stages will have different kind of delays. Let's say here it is S1, then interface, then it's S2, and then there is an interface, then there is S3, then there is an interface, and then we are going to have one S4, which is like this. Now, considering the entire scenario with the clock and everything, what we are going to have, we are going to have different stages. So different, let's say this particular stage is having 2 nanoseconds of time delay, then this is 3 nanoseconds, let's say this is 4 nanoseconds, and let's say this is 5 nanoseconds. So here what we are going to do, we are going to take the maximum of the stage delay. So here 2, 3, 4, 5, we are going to take the max of these all. So here it will turn out to be 5 for us. So we are going to consider the maximum of the stage delays encountered by every stage in the non-uniform delay. Okay, so if the buffer is included, then we are going to include the buffer's delay as well, otherwise not. So here the max delay will be 5, and here the max delay will be 5 plus, let's say it is 1 nanosecond for every particular interface. So 5 plus 1 equal to 6 is the answer here. Okay, so we are going to consider these questions in both uniform as well as in the non-uniform. So when you are reading the question, be aware that whether it is encountering the non-uniform delay pipeline or it is going to talk about the uniform delay pipeline, because then the answer will be very much changed, just with the fraction of values that are being changed here. Okay, so that was all for this video. In the next video, we are going to discuss concepts of the pipelining, which are actually the dependencies in the pipelines which are created. So as we know that the pipelines are executing in the overlapping fashion, so there will be some kind of dependencies which will be encountered as well. So in the upcoming videos, we are going to discuss about the dependency in the pipeline. So that was all for this video. Thank you.